Okay guys, so welcome back. Today we have lecture 20 and today we're going to look at a system of first order ordinary differential equations. So instead of just having one equation, we can have a system of linear differential equations. So the same thing as you have a system of equations, you can have a system of first order ordinary differential equations. So often engineering and science problems are governed by a system of coupled ordinary differential equations. So the term coupled here means what? Is that if they were uncoupled, you could solve one equation at a time. Okay, but if they are coupled, you need to solve both equations at the same time. Where the unknowns y1 of t, y2 of t to yn of t represent state variables. Okay, so these state variables will be generally different properties or characteristics of a system, like pressure, force, current, etc., etc. All right. So let's jump right away into a system of ordinary differential equation and see what happens. All right. So let's see what would happen over here. So given dy1 dt, so this will be our first equation. Let's say it will be in function of f 1 t1 y1 y2 to y sub n, dy2 in function of t dt would be f2 t2 y1 y2 y sub n. If we have n first order differential equations, okay, this would be the form of our system of ordinary differential equations. Okay, or I can just rewrite this system in a more compact form or in vector form. Basically what we have, all these equations over here would be what? Dy dt of t. Okay, and this should be equal to what? To a vector of functions, so it would be a vector, all right, of f of n in function of t and y. Okay, and this should also be a vector over here. and a set of initial conditions y of 0 would be then y1 of 0, y2 of 0, up to yn of 0. Okay, we can just call this one y sub n. Alright, so let's see. Let's go to the next page. Page 138. Okay, so if the system of ODEs is linear, the solution exists and it is unique. Okay, so the solution y of t will be of the form of what? y1 of t, y2 of t, until yn of t. Okay, so now let's just rewrite what would be a more general form of a linear system of ODEs. So a linear ODE system can be expressed as what? So let's say we have dy1 dt of t could be equal to a coefficient that can be constant in function of t, so a11t 11t plus a12t y2t until a1n t yn of t plus, let's say, another function here, j1 of t. The second one could be dy2 dt of t will be equal to a21 of t y1 of t plus a22 of t y2 of t plus a2n of t yn of t plus a function g2 of t, and we can do this up to a function tyn dt will be equal to a n1 of t y1 of t plus a n2 of t y2 of t plus a n of t yn of t plus gn of t. Okay, so this would be our system of ODEs, or again, or in vector form. This will become what? We have here dy dt will be equal to a matrix of coefficients A, okay? And then we have this would be time a vector y of t plus a vector of g of t. Okay, or in a more compact way, we can just say this would be y dot of t equal a of t y of t plus g of t. Okay, with the brackets here means a vector. So this will be the general form of the system of a linear ODEs, and here where you're gonna have a of t over here will be equal to what? A11 of t, A12 of t, up to A1n of t, A21 of t, A22 of t, up to A2n of t. Then we can go down to A n1 of t, A2n of t, up to A and n of t over here. Alright, so this would be the matrix of the coefficients. Okay, and then what can we have? Well, maybe give me an expression for these two. Page 139. So basically, vector y of t will be equal to what? y1 of t, y2 of t, up to yn of t. Okay, and vector g of t will be g1 of t, g2 of t, up to gn of t. Okay, so now let's go to special cases. So if g of t equals 0, that means what? System of ODEs is the right hand side will be equal to 0. Okay, so that means that is homogeneous. Then if the coefficients are constant, so let's say this means what? System, so coefficients are constant and are not in function of time. So in that case, this equation here, okay, we can write that equation under which form? This will be constant in function of t, and this will be 0 over here. Okay, so we can just write down that so that the equation becomes what? Y dot of t vector will be equal to the matrix of constant coefficients A times y of t. Okay, so this is linear homogeneous constant coefficients system of ordinary differential equations, or ODEs. Alright, so before we learn how to solve this type of system, let's just look at what happened with just one of these functions. Okay, so let's over here, let's call this preliminary. Okay, so let's say instead of having a system of ODEs, we're just going to take one. So given the ODE dy dt of t equal ay, okay, and y of 0 equal to 0. So this ordinary differential equation is linear, homogeneous, and of the first order. Okay, and we have this initial condition to be y of 0 equal to 0, so this becomes an initial value problem. Okay, so find solution y of t. So basically solve the equation. Alright, so what is the function that when you take the derivative gives back itself? Okay, so we know that the general solution for this ODE is of the form y of t would be equal to what? Let's say to a constant e a of t. Okay, and we can test it now. So let's say you assume the solution, and what we're doing here is what will be done almost in every single procedure when you go and solve differential equations. You assume the solution and then you tune the solution by finding the value of those different coefficients. Okay, so let's go and check if this is a valid. Let's go and check if this is a good solution, or a good assumption in order as a solution for this ordinary differential equation. So page 140, let's go and check. So let's see, what are we doing now? So we have the equation dy dt equal ay, and we're assuming that y would be equal to what? Would be equal to c exponential a of t. Okay, so this will mean what? If we look at this side, we'll have d dt of the assumed solution, c exponential of at, and this needs to be equal to a of what? What of y, which is c exponential of at. Okay, so from here you can see right away that if you take the derivative of the exponential function, you will have a times c a exponential at, and this will be equal to a times c a exponential at. Okay, so you see that this is check. So the assumed solution works. Okay, so once you have the assumed solution, now you can go and say, okay, the general solution is this one. So general solution is y of t equals c exponential a of t. And now in order to find the particular solution, we need to apply the initial condition. Okay, so let's say applying initial condition, which is what? Y of 0 equal to 0. This will give you that 0 equal c exponential of 0. Okay, so you know that the exponential of 0 is 1, so this will give you that c equal to 0. And that is a problem, because what is the problem? Is that now that is indicating that the solution, the particular solution, which is what? Basically y of t equal to equal to c exponential 8t is equal to 0. Okay? And this will give, if we go back to the differential equation, 0 equals 0. So that's not good. So this is what is known as the trivial solution. Let me write over here then we'll have that dy dt equal to a y will give what? Will give 0 equal to 0, which is the trivial solution. Okay, so obviously every ordinary differential equation, if you assume that the solution is 0, it's always going to be 0, but that's not the solution that we're interested on. So what is the conclusion that we have over here is that if we solve a system of first order differential equation, at least one of the initial condition must not be homogeneous or equal to 0, okay, in order for the solution to exist. So let's write down that. So therefore, if the linear / homogeneous ODE system given by what? Let's write over here y dot of t equal to the constant coefficients y of t. So therefore, if the linear homogeneous ordinary differential equation system given by this equation has a solution, comma, at least one of the initial conditions must be not equal to 0. Okay, so basically that will mean that the vector y of t is different than 0. Okay. Okay, so basically if you have the initial condition equal to 0, the equation will give you 0 equal to 0, which is a trivial solution. So that solution, it is a solution, but it's not the solution that we are interested on. Okay, we'll be interested on the other solution. All right, so let's go and try to find what would be the general procedure in order to solve a linear system of ODEs. Alright, so since we know this for one equation, we can make the assumption that now that an analytical solution of a system of linear homogeneous first order ODEs may be attempted by recognizing that the general solution of a single ODE is what? Basically what we just did. So what was the solution? Is so for example we have the ODE dy dt equal a of y. We found out that the general solution y of t was of the form c exponential a of t. Okay, so it would be logical now to say, okay, this is the solution of one of them, this might also be the solution of all of them, or at least the solution to all of them will be also of this form. Okay, therefore, comma, it might be infer that the solution of a system of ODEs, okay, would be which form? So we'll have this time y of t will be x e lambda t. Okay, and I will explain now what is each one of the terms. So basically we're not going to have just one constant over here, we're going to have this vector of x over here, but it's about the same form of c exponential of aat. Okay, so in that equation, where in this equation lambda is generally known as the eigenvalues and x over here will be, so this will be alpha 1, alpha 2 up to lambda n, and this will be the eigenvectors. Alright, so we have here, let's say, eigenvector corresponding to the first eigenvalue, eigenvector corresponding to the second eigenvalue, and eigenvector corresponding to the n value, okay, to the n eigenvalue. Okay, so I'm pretty sure you heard the terms eigenvalues and eigenvectors before, so you will see that the whole thing about solving a system of first order linear ODEs is about solving the eigenvalue eigenvector problem. All right, so now let's go to the general procedure on how to solve a system of ODEs. So procedure to solve system of first order ODEs. Okay, and here I'm implying that the system of ODEs is linear and homogeneous. Okay, so first step is always to assume the solution. So as we said before, the solution will be of which form? So assume solution to be y of t equal x e lambda t. All right. The second step now is to substitute the solution, so the assumed solution, into the ODE system. So that means what? Let's say we have the system, which is y dot of t will equal to the constant matrix of coefficients times y of t. Okay, so if we substitute, what do you get? We did it before, but what will be dy dt? Dy dt will be equal to lambda x e lambda t, and this will be equal to a times y, which is x e lambda t. Okay, I think you know how to do that, but let me just do one little thing over here just for clarification. Okay, so this is equal to what? This term over here, y dot, is equal to d dt of vector e lambda t. So this is equal to what? Function of t will be equal to lambda times our vector x e lambda t, okay? Which is this term over here. Alright, so now you can see right away that since you have e lambda t on each side, you can cancel out, and we are left over with a lambda x is equal to lambda times x again. Okay, so that's an interesting equation, because this equation represents the definition of an eigenvalue slash eigenvector problem. Okay, so the eigenvalue, eigenvector problems are not difficult to solve, but the understanding is sometimes a little bit more tricky. Okay, so what is the meaning of this equation? Okay, I'm going to try to explain it with a simple example. Basically saying that this is thing about a vector. Okay, a vector has a direction and a magnitude. All right, so the eigenvalue shows you the if you want the value of the vector, let me rewind my explanation. Okay. So let me take an example. So the eigenvalue problem. Let's say you have a beam, simply supported beam over here, and you want to calculate what is the deformation of that beam due to a force that is applied. Let's say it doesn't matter where you do it, but for here I do the simple case is apply in the middle. So we all know that the shape of the deformation will be this. Okay, so the eigenvalue problem, what it's showing you is that this is a vector. All this here will have different vectors direction. So the shape of the deformation of the beam will always be the same, okay, independently of the magnitude of the force. So depending if F is very large, it might be here. If F is small, it's over here. We could be over here. But the general shape of the deformation will always be the same. Okay? The only thing that will change will be the magnitude. So the distance between here and here, here and there, and here and there. So the eigenvalue eigenvector problems will never give you the magnitude of the deformation, how far is this curve over here, but it will always give you what is the shape of the deformation or this or whatever parameter you're trying to find. So mathematically speaking, this means that if this is a vector, x is a vector, the eigenvalue will always give you the direction of the vector, but never the magnitude. And as you know, there is an infinite number of vectors that will give you the direction of a vector. So in other words, if you have a vector here into this current system, if this is the direction of your vector, all right, there's an infinite number of solutions, because you can have this vector will be a solution here, this one will be a solution, then if you go here, this will be also a solution, this one will be a solution, and so on. So what I want to say is that this line will correspond to a specific value of lambda, okay, given the direction, but it will be an infinite number of eigenvectors giving you that direction. Again, this might not be clear because I told you that the eigenvalue eigenvector problem is not very easy to understand the concept until you start using it. I think the easiest way to understand is probably this one over here. It will give you the general form of the deformation, but it will never give you the magnitude, okay? Because it will be an infinite number of curves that will satisfy this one, but the magnitude will depend on the initial conditions of the problem. So I hope that did help you a little bit. Okay, so let's not lose track over here. First thing to do is to assume the solution. You substitute into the system of the ODEs, and now that means that this is taking us to solve an eigenvalue and eigenvector problem. So that's what we need to do now. So page 142. All right, so we can rewrite or in matrix form so this equation here, I'm just going to rewrite it. A lambda vector x equal to lambda x. All right, this really is equal to a x, and here we only need to take the diagonals of this term. So this will be the identity matrix times x. All right, where the identity matrix here, you know, will be equal to 1, 0, 0, 1, 0, up to 1 over here, and this will be 0, 0, 1. Okay, so then what happened? The equation over here that we have equal lambda identity matrix X. This one we can just write it as A minus lambda times the identity matrix, both times X will be equal to 0. Okay? So, for the above equation, to be satisfied, what needs to happen? Okay, so for this equation to have a solution, again we have two cases. So what would be the easy solution? Do you remember before we mentioned the trivial solution? So in that case, what would be the trivial solution? If x equals 0, then we have 0 equals 0. And again, this is the trivial solution. That we're not really interested in that type of solution. Okay, so the other solution is that this term over here is equal to 0. Okay, so for that to happen, okay, you need to have that the determinant of A minus lambda of the identity matrix to be equal to 0. Okay, so now the solution of the equation given by this equation here, by the determinant of A minus lambda of I, is known as the characteristic equation. Okay, so now solutions to that equation, which is the characteristic equation, yields to the eigenvalues. Okay, so now that we have the eigenvalues, what do we need to do? Oops, sorry for that. Hold on 1 second. Okay, so hope you have time to copy this. So now that you have the eigenvalues, we can find the corresponding eigenvectors to each eigenvalue. So I guess that is step number 4. We did steps, let's see. One, 2. Okay, so this is step 3 really, to solve the characteristic equation. Step 3, and step 4 is to solve the eigenvector x for each eigenvalue lambda. Okay, so how do we do that? So what you need to do is substitute each eigenvalue back into the equation. So the equation that we had before, which is A minus lambda times the identity matrix times x equal to 0. So for example, here you will say for lambda equal to lambda 1, okay, this will have a different value. So again, the solution of this system will be x equal to 0, the trivial solution, which you are not interested, or you can find the values of x1 and x2 that will give you this equal to 0. Okay, so you will solve here for the first eigenvector corresponding to the first eigenvalue, lambda equal to lambda 2. You will solve for the eigenvector corresponding to the second eigenvalue, and you can do this up to the nth eigenvalue. Okay, then 5, you substitute the eigenvalues and eigenvectors into the assumed solutions. Okay, so remember the expression for the assumed solution is y of t equal to x e lambda t. Okay, so that gives us what? y1 of t will be equal to x1 e lambda 1 of t, y2 of t 2 will be equal to x2 e lambda 2 of t, and we'll have this up to yn of t to the n will be equal to the eigenvector to the n root e lambda n of t. Okay, so if you remember, at the beginning of this chapter, we mentioned the principle of superposition. Okay, that means that if one equation is the solution of one differential equation and another equation is the solution to the same differential equation, you can add the solution and this will also be the solution of the differential equation. Okay, so I'm using the superposition principle, the general solution y of t is a linear combination of the ones above. Okay, I'm going to put you in pause for a second and see if I find that first page. Okay. Okay, so I found it on the class notes. If you go back to page 100, we wrote over here a superposition theorem that basically says if y1 of t and y2 of t are both solutions of the same homogeneous ODE, thus the total solution will be A y1 of t plus B y2 of t. Okay, so using that principle, we can do the same thing over here, and in that case the total solution will be what? Will be the summation of all these different solutions. Okay, so we'll have over here y of t will be equal to y1 of t plus y2 of t plus yn of t, or I need to add the constant over here, c1 eigenvector 1 e lambda 1 of t plus constant 2 times eigenvector 2 e lambda 2 of t plus dot 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 up to cn x n e lambda n of t. Okay, so this will be over here the general solution of our problem. Okay, so let's see, that was page 143, page 144. Okay, so step 6. Using initial conditions, we're going to solve for C1, C2 up to C sub n. Okay, and once you have C1, C2, C3, C4 up to C sub n, you can just go back to the general solution and substitute. So really that should be the last step. 7, substitute constant coefficients, C1, C2 up to Cn into the general solution. Alright, so let's see, this video is about 54 minutes and we need to do one example. So I think I'm going to break this lecture in 2 parts. This will be the theory and then I do the example on a different video. Okay, so I'm going to stop this video now, but again, this lecture will have 2 different videos.